Okay, so you have these two things. You have a crop increasing fertilizer, CIF, and the yield enhancing cultivar, YEC, and we want to see which one is better. In fact, we want to test to see if the CIF is more effective. So that's what we're looking for. So state, we would restate this, okay, and then we have to establish our variables. So here's our two variables, the true mean tomato yield for the CIF and the true mean tomato yield for the YEC. Okay, now don't forget we need the random, normal, and independent. I think we know how to establish those. Now for this one, sample size is 10, so we can't use the central limit theorem, but that's why they show us these graphs over here. They show the graphs that show that they are approximately normal in shape. There's no skewness or outliers, and that would be for normal. Okay, let's do the math part, the do. So this is going to be a two-sample t-test. So let me write out the math part. And here it is. So this is our what we expect if our null hypothesis is true, right? Oh shoot, we didn't do the null hypothesis. Let me do that. So there's the null hypothesis. If we subtract the two, if they're equal, you get 0 versus if you subtract the 2, remember, we want the CIF to be bigger, more effective. We're going to have a number that's bigger than 0. Okay, that's important, right? Oop, don't forget the alpha level is going to be 0.05. Okay, so now we've done all that stuff. Here's what we expect if the null hypothesis is true versus what we observed. Here's our standard deviation. Square them, add them, right? Take the square root, and the sample size. Now we're not going to pool because we would only do that for a proportion, and this is a t distribution. Okay, now what I'm going to do is I'm going to put it in the calculator. Let's see, the degrees of freedom would be, what, 1 less than, so we would use like 9. But I'm just going to use a calculator and put it in. So what I do is stats over to tests, and I am going to use a 2-sample t-test and put all the information in. So I'm not using data this time. I'm going to use the stats because they give us all the information right here. We wouldn't put anything into list 1 and list 2 anyway. So let's see what we get. So I put it all in the calculator, and it gives me a t value. So all of this stuff right here, if I did all of this stuff, I would end up with a value of 2.24, 2.24, which gives me a p-value of 0.02. And the degrees of freedom, it's important to write that down. You said I used technology to get this. 14.3 was the degrees of freedom that the calculator came up with. So there's the do part. Now what does that tell us? Well, we are going to reject the null hypothesis at a 0.05 alpha level in favor of the alternative hypothesis and say, yes, it looks like the crop increasing fertilizer is doing a better job than the yield enhancing cultivar. Okay, there you go. So you might write something like this. Since the p-value is less than 0.05, we have sufficient evidence to reject the null hypothesis in favor of the alternative hypothesis. It appears, see, I'm not committing anything, it appears that CIF may be more effective in tomato crop yield than YEC. There it is. There's number 4. Okay, let's see. What do we have here? You might look at this one, since it's been quite a while, you'd be like, wait, what do I do with this thing? So the mugs, each mug has a weight of 6 ounces, standard deviation of 0.2, and each of the calendars are are 8 ounces, standard deviation of 3, and the box is 3 ounces, standard deviation of 1. Okay, and what do we get for this? Let's see. They shipped this 5 desk calendars and 4 coffee mugs. Okay, so what's the whole thing going to weigh? So we might write it like this. So this is for the whole package. We got 4 coffee mugs, 6 ounces each, 5 desk calendars, 8 ounces each, and just 1 box for the whole mess. And so that's going to be 67 ounces. Now let's do the standard deviation. So remember, we square them, we add them, and we take the square root. But remember, there's 4 of them. There's 4 mugs. Each one has a standard deviation, could be off by 0.2. So 4 times the standard deviation, square it. 5 calendars. Each one has could be off by 0.3. And then don't forget that we need to take the square root of this whole thing. And then that's going to give us our new standard deviation. Okay, so that's the answer for letter A. Now it says a firm is charged additional postage for a package that weighs more than 68 ounces. What is the probability that a randomly selected package will be more than that, right? Require additional postage. So what are we going to do with this thing? Let's see. It's kind of a z-score, right? Here we go. So it's the number we're interested in, that's the 68, minus the number that we expect, which is 67, right there. And we're going to divide that by our new standard deviation, which is 0.79. So the answer we get is 1.265. What do we do with that? Normal CDF. Yes, normal CDF. So here we go, normal CDF. Normal CF goes from negative 1,000 to 1.265, and that gives me 0.897, okay? But we want to know if it's bigger than that, right? So we're going to subtract it from 1. 1 minus 0.897 gives us about 10%. Okay, 10.2%. Whoops. Okay, so there's about a 10% chance that you're going to have to pay additional postage on this thing. That's our conclusion. So now, what if we take 4 packages? So the only thing we need to do now is figure out the new standard deviation. So our old standard deviation was 0.79. So the new standard deviation is 0.79 divided by the square root of how many you have, which is 4. So let's figure out the new standard deviation. So the new standard deviation is going to be 0.395. Okay. And then we do the same process. So the average weight, right, is, let's see, over 68. That's the number we're interested in. 68 minus 67 divided by this new standard deviation, which is 0.395. Same process as that, normal CDF, subtract it from 1, and you should get 0.0057. So a less than 1% chance that if you just take 4 random boxes, that their average weight is going to be over the, 67, right? No, it's over 68. That's what we're looking at. So there it is. That's a tough one. You got to remember how to do that one. So that's good to look at.